We stopped at triple modular redundancy and modular redundancy last time. So, next step. What can you replicate? What redundancy levels can you imagine? What can you duplicate? We discussed this a little bit last time. You remember what we could replicate? You want to replicate computers, obviously. Anything else you can replicate? You want to make sure that if you have a modular redundant system, that the same fault does not occur in all of your systems at the same time. Does that make sense? Okay. So if you only do this one step of cloning the same system 5 times, how high are the chances that those 5 systems are falling over exactly at the same time? Pretty high. Why?
Because it was the fault in the first system. They're identical. It's the same code.
What kind of faults are you protecting against if you just clone your system 5 times?
Hardware failure.
Some forms of hardware failures. When you assume that the CPU is melting in one but not in the other, then that makes sense. So assuming that you want to be protected a bit better than that, how are you managing this replication? Where do you put variance in there?
Replicate the sensors, or anything feeding data into the computer.
Yeah, so the first thing, you're not only replicating the CPUs, you're also replicating the sensors. Now you assume that all of those sensors are not failing over at the same time. Are you using the same programs in all of these computers?
You mean if you only have one program?
Yeah. That's actually a very hard question. Put yourself into the shoes of somebody in industry and you have to explain to your boss, I want to have 5 different programs solving that problem. I want to have one program, which I think is right, solving that problem. Which one would you prefer? You have a budget. There's only a limited amount of money available. You would throw your budget at one and do it right?
You can have one with like a backup safety software thing. It's not really doing the exact same task, but it's doing some sort of checking functionality.
One with some checks and bounds around it, some exception handling around it. Okay.
Or maybe your backup system, if it like being told to run like this is terrible, something crazy has happened, shut down safely, or like cease operation or safe manner. Like if you're a server farm, don't just shut off everything. Try and like tell everything to shut off. Don't use all the things.
Get some guys halfway across the world to see what they would do. Anything correct to what we would do.
And not telling them that you have a budget, just motivate the open source community to do it all for you. Huh? Okay. Maybe. Okay. This is what is done. Usually, and we talk about this in a moment, you're starting from the same specification, and even that is not 100% clear. Then you go to different manufacturers and buying your CPUs, a bunch from AMD, a bunch from ARM, a bunch from Intel, and you diversify your hardware platform. You buy different memory modules from different manufacturers. Of course, you run different operating systems on them. Different languages, different programs. And it's the opposite end of what you want to do. This is the approach of, if I diversify everything, I just have a higher statistical chance that they are not all falling over at the same time, which is what drives that. what do you do if the outputs are not in perfect agreement? Because with that level of diversity which you have here, what are your chances that all of your CPU lanes are reporting the exact same value at the exact same time? Pretty slim. So there will be variations, and you have to model that. You have to make sure that that's all right. This one said 3.99, this one said 3.98. They mean the same thing. You need to actually model that this is in tolerances, this is fine, this is not fine. Because you cannot just do it as a binary comparison anymore. Not with that kind of diversity. Concrete example. The Boeing 777, which most of you will have used in the past. The target probability was has to be safer than 10 to the power of minus 10 failures per hour. Put this in relation. Seaswell Block B nuclear reactor in the UK is spec'd to 10 to the power of minus 3 falls per hour. And then it got its certificate. Aviation is a few orders of magnitude beyond that in terms of what is an acceptable level of faults there. And this is a level of fault which is quite non-trivial to achieve in the real world, because you are below that with many hardware components in your system. If you just add up or look through the data sheet of your hardware components, 10 to the power of minus 10 is something which is pushing it already. In those kind of areas, you have to assume that many of your components, particularly most of your sensors, are falling over before that. Which means sensor replication is a very first thing which you have to do before you can dream about getting anywhere close to something like that. What have they done? 777 is not exactly a current design, but the 787, which is the latest model, which you hopefully have been flying, very comfortable plane actually, is using the same controller setup, not the same CPU hardware anymore, but the same overall setup and the same control structure. As a matter of fact, they have been trimming and training the 787 controller live in the loop by emulating flight behaviors and surface behaviors of the 787 on board the 777, and have been trimming the flight computers for the 787 while flying a 777. As I said, first thing, diversify loops. Diversify CPU lanes. Back in those days, it was AMD Motorola. You probably don't remember that thing, Motorola 68040. Quite old CPU. It's not about speed. It's not about performance. It's about reliability and diversity here. And of course, IMUs and power sources are independent. Goes without saying. Different compilers. And the interesting thing is, they also investigate the possibility, and we will do this in a moment as well, different programming languages, different environments, and Boeing came to the conclusion that it's not worth it. Do one source code right. And they actually nominated the source code its own specification. They removed actually the specification for the whole thing and said, this is the reference code. It's supposed to work like that. Which is of course clever, because it will work like that. But they also made sure that this is identical to what they want. And evaluate against exactly that one. And it was a clever comment, don't remember who said that. Same compiler, but different, and same source code, but different monitor functions, different exception handling code to go around that. So the core code is identical, but the monitoring code is diversified around it. Does this work? Check out the aviation news, if you're brave. So one of the sources which is always open on my browser is the Aviation Herald. But as I said, this is a one-way street. Never look there if you're afraid of flying. Where all reported incidents on a daily basis are turning up there, which is very interesting. See how many faults and what kind of faults are actually turning up. To my knowledge, the 777 didn't have any kind of controller failure ever. And individual line failures, of course, it's designed for that, but not an overall controller failure. And not only on that kind of design, but also the related kind of designs. An actual outage of a flight controller has never led to a catastrophic failure in aviation history, which is a very, very strong statement, considering how many flights, how many planes are in the air at any given time. This is quite amazing. Unless you open up the Aviation Herald and you see some news which are contradicting that. On average, we have about 10 incidents per day worldwide, and every 2 or 3 days you have something more severe, which is categorized as an actual accident, which means that people got hurt in the process. It doesn't mean that anybody got killed. It can, for example, mean excessive turbulence and somebody was smashing the ceiling someplace, which happens very regularly. So,
we're having a look, and there was a bird and rabbit strike at the same time in Melbourne. It didn't happen anywhere else in the world.
yeah, you get used to the more common things, bird strike. Tail strike is much more frequent than you imagine. Tail strike, that you touch down with the tail on landing. And engine failures are reasonably common. Happens about every 2-3 days when you have actually an engine failure or flame out someplace. And because they have multiple, so it's not a single engine world which we are flying, we have usually more than one.
So the details were, it was an eagle carrying a rabbit.
Really?
Yeah, bird and rabbit strike at the same time.
All the comments are just talking about it.
Well, actually one of the most common failures for engine failure at all. And unfortunately these bird strikes are quite scary in the sense of if you lose an engine while you're at 10,000 feet, it's much less scary than if you lose an engine when you're climbing out. And this is where the bird strikes are actually happening, because you're the most volatile just in the first turn, when you just get a little bit, and then losing an engine is a very scary maneuver, which you have to pull down. All right. As I said, the aviation world in that sense is very open and transparent, because you have a legal duty that all of these things are reported in a quite formal way. The Aviation Herald is just more of a news site, collecting all of these kind of things. All of the aviation authorities, the FAA and the European counterpart, they all have their own websites where you can read the full reports over that one, if you can stomach that. So some of them are, of course, quite detailed. And as I said, if you're afraid of flying, don't consider going to any of these pages.
Still significantly less than dying if you can't drink immediately.
Yes, but as humans, how much are you able to model those statistical chances and possibilities?
I can compare.
And that makes you actually feel more safe?
Yeah.
Oh, that's good. That's interesting.
I know that's not normal. I know that people like much more afraid of turbulence in an aeroplane than they are, getting T-boned as they blow their drag. If I can sort of see one or two of the raw numbers, you can reason it much easier.
Are you scared driving a car? participating in traffic?
Only
Yeah. Yeah. Certainly. I was always in the feeling that, or the saying, if you learn driving in Europe, I was learning in Paris and other places where you have lots of cars and they're going pretty fast. Learning to drive and guiding a car, you have one foot in the grave and one foot in the prison. That's the feeling which you have going in there, and this is always there. There's always a chance that you make a very brutal mistake someplace, or that somebody else makes a very brutal mistake very quickly. And the road fatalities, by the way, in Australia are going up again. So the myth of roads are becoming safer and safer are simply not true. The number of fatal incidents is actually on the rise again. I leave it to your imagination to explain why. Maybe people are feeling more safe with their 27 airbags now and have less an idea how to drive physically, as opposed to flying an airplane where most people, or half the population, are scared of, because that's so dangerous you can fall out of the sky. But the statistical relation is just not sinking in between these things. Anyway, if you work in safety critical environments, these numbers and the chances how often you fail are a concrete number which you need to model and live up to. You have to guarantee these kind of things, and you have to give models for that. Why are you coming up with that kind of integrity and safety? Inversion programming. Now, for a second, assume we want to diversify the programming. This is just a little colorful illustration which part of the programming phases, specification, design, coding, or testing will be affected by different variations here, because different coding can express itself in different compilers, different languages, different methodologies, different design approaches. You can throw the whole book at these kind of things and design your programs completely different. Is that a good idea? Does that make sense? 1992, UCLA ran an interesting project to test that. The 6-language project that just modeled a reference flight controller with a team of with 6 teams, 6 programming teams in 6 different programming languages. They isolated all the programming teams against each other very strictly. They were forbidden any kind of communication. Why?
very different designs.
Even if you're not talking explicitly about your solution, there's a very high chance that a misconception, a misunderstanding of the specifications is migrating by simply communicating in any form about the project at all. So they're strictly separated. You're also usually trying to get these programming teams hired from different places, from different countries, in fact, from different universities in different countries. Why? Yeah, actually different teaching methodologies, actually different philosophies at the time. You have the hype language in France at the time, you have the hype language in the UK at the time, and this influences the thinking of whole generations of programmers. So if you want to diversify that, you're actually hiring people from different universities and different countries to go into that. Communication was completely formalized. They could only communicate with the coordinator to ask questions about the whole thing and get back to that one. Hopefully the coordinator itself did not distribute that one. And inversion programming was applied to all of the development stages, but diversified in any possible way. Now the programming job itself is not particularly high. I think that was a fighter jet controller, as far as I remember. They've been doing that. And those were the 6 languages which were chosen at the time. Some of them are prehistoric now, but those were the languages which were tested there, including some Lisp dialect. So completely different approaches to that one, including Prolog, which was a pretty strange choice for a flight controller, but it's about diversity. Let's try to test all these different possibilities. Lines of code, you have to see this with respect to the language, so that doesn't say much. It's just it's more saying more about the language than the concrete implementations. And then it was tested against the Golden Master environment, which was provided by Honeywell. And we counted up the number of failures into the individual programming languages. And here's not the question which programming language produced failures or not. The question was, they already knew that not all 6 of these projects will deliver a fault-free solution. That was the point of it. And what do you do with this kind of information? You look at what is the chance if I now implement on the actual airplane a 3-version controller. Then I take at random 3 of these implementations and run them on 3 different pieces of hardware. What are my chances to get single errors and the chances to get coinciding errors, or if that you get actually 3 errors on the whole thing? If I have a 3-version system, single errors I can ignore because they will be voted away. And I only look at the possibility for individual errors. And yes, you can actually press it down quite significantly. What did they learn from that? The Golden Master version from Honeywell was actually superseded by both, by the 3-version and the 5-version alternatives. So the single, where they put all their buckets in one, all the eggs in one basket approach, was actually outperformed by that in practical testing in real life. It is also only possible because they use students for that. They didn't pay these kind of guys. As you can imagine that if you have a complete budget at hand, the decision of a 6-version implementation means you go into the office of your boss and you tell your boss, look, the budget just multiplied by factor 6. Because this is what it boils down to. And that's a major investment. Now, if you go to your boss and say, look, my budget doubled because I want to have one version, which I want to test a lot better and put more effort into that one, that could give you possibly a similar result. Or if you say, I put 6 times the money into one version, it's not quite clear whether you're actually getting further with that or not. Let me get back for a second again. The specifications for the whole thing. The specification which I used here was a little bit enhanced and diversified. What does that mean if you diversify a specification? Why would you do this in the first place? It sounds bizarre. Diversifying a specification. So if you do this, you do that. It turns out in practice that the formulation of the specification so frequently leads to unintended misinterpretations in the design teams that a very promising part of solving your problems in a high integrity environment is providing multiple specifications which have been carefully reformulated to express logically the same thing in very different ways. If your specification is formal to start with, that's nice. But even then, the way how you actually express that could trigger different interpretations. Because ultimately, you're still humans reading that and trying to come up with an implementation for that.
What sort of representations do you make? What sort of interpretations? Are we talking literal English or?
Yeah.
Okay.
Yeah, those was just literal English. And just the way how it is formulated can lead to very different ideas, what you're supposed to do. Even though it's logically clean and correct, so it's not that the specification is formulated in a faulty way, but the specification is just suggestive in a certain way. So you have to diversify that in a sensible way. That's probably a level of diversity and high integrity programming that would have never entered your mind before. Because, well, that's the reference. My client wants me to do that, but you're questioning that, you're reformulating that in a number of different ways so that you can then design it in a diversified way. Doesn't help against all possible faults, but quite a few of them. Now, a few issues about this end-version programming, because you need for end-version programming some kind of a voting system. You need to make sure that 4 out of 5 of my CPU lanes came up with the same result. When is this actually the case? Now, if you have integer arithmetic, that's usually fairly clean cut. At least you don't have any, if you don't have any overflow surrounding anywhere in your fixed point integer arithmetic. If it's long enough for the whole thing, then you can simply binary compare your results. And you hope that the timing of your results are also comparable, which is not quite clear if you have different clock frequencies, different CPUs, different hardware architectures to calculate those numbers. If you have real arithmetic, obviously you have to have tolerance bands for this whole thing, because real arithmetic will almost always drift away in one way or the other. Having said that, most of the CPU architectures you buy today are just slavishly implementing the IEEE floating point standard. And if you do that, in reality, usually the floating point results are actually identical. Modular all the translation mistakes when they translate the IEEE floating point standards into complete hardware. But the idea is that the results are actually the same. But then comes the more interesting problem. If your computers are actually diverting in different directions, does this necessarily mean that one of them is wrong? We're talking about very, very simple controller systems here, where you can apply something like that. If you, for example, have a navigation system, a path planning system, in your car, if you switch on the navigation system, and you have 5 of your navigation systems, will they suggest the same route? Most likely not. At least if they're not based exactly on the same software, the same map background, then chances are very high that they will suggest different routes. At least on the fine-grained level. They will divert a little bit. But they all can be perfectly correct in terms of getting from A to B. And in many environments you have exactly that kind of situation, that the solution which you're getting is valid, but not bit pattern identical to something else. How do you compare multiple valid solutions with each other? This comparison can be way more complicated than the actual algorithms you want to protect against. If that's the case, sounds dangerous. For end-version programming, That's usually not considered. For n-version programming, you're redesigning your problem so that the answer is actually unique. So, yeah, we already talked about specification. If default is actually in the specification, and depending what kind of reports you're reading, but it's a substantial amount of real-world faults which are going into specification, all of this is void. None of these approaches will give you any head start at all. And there's a diversity assumption around that one. That diversity is actually the case, not just on paper or in your mind, but you actually diversify things. All the critical things should be diversified. And you have to be critical about this, whether this is true in the real world. As I said, such social contacts can make a lot of your interactions void. If you remember the slide for the 6 language projects, in very different languages, these teams made exactly the same mistake, using very different tools, very different methodologies. Now, the fact that somebody in a Prolog design team comes up with exactly the same flaw as somebody programming in a C design team is actually quite interesting. All this diversity did not avoid that some of these errors were actually coincident. They misinterpreted the specifications exactly the same way, despite everything else being different. And the final part is project cost. Putting your money into 6 underfunded wobbly projects, or in one solidly funded project where you can do your job right. So, dynamic redundancy, what do you do to handle problems if they occur in your system? You have to implement a number of different things, and possibly at least the first 2 you have to implement. Error detection. How do you find out that your system is off track? Once it hits the ground and you're in a fireball, it may be obvious enough, but can you catch it a little bit earlier than that? Yeah.
You see what everyone for the auto controls is saying, for example, if you're about to say something way off, you can somehow figure out what you're doing wrong?
Yeah. If it's actually caused by your controllers in the first place, there's another error in your system which is outside of the controllers, how do you detect that? Next level, damage confinement. Finding out how far that reaches, and can you contain that? Can you reduce your error to not affecting other parts of the system? Can you isolate it? Redundancy. Error detection. Error detection can mean that you throw more hardware in your system. On the software side, how do you detect errors in your software? You have all the classical methodologies on the screen here. Replication we already talked about. Timers, that means you have wrapping code around most of your critical sections. If this takes longer than this and that, something's wrong. Or you have watchdog timers, hardware timers, around your system, which you have to reset on a regular basis. If they're triggering, if they're kicking you, something's wrong. Then more software-oriented things, which you all have been doing in some way or another. Apply the reverse function. See whether it actually translates in the other direction as well. Translate it one way, translate it back. Do I get the original result? If not, something's wrong again. Coding redundancy. Applying Hamming code, CRC checks of some sort. making sure that you're not losing information in that level. Contracts, reasonableness. You have possibilities to check your results against some rational predicate to want to hold up and make sure that it's true at all times. You can wrap all of your code into those kind of contracts. And integrity, you have your type invariance. At any given time, something has to be holding true for my type structure, for my data structure. Yes, invariance applied as well. Both of them you can implement directly in your Ada or any other contracting-based environments. Continuity, very frequently applied in real-time systems. You assume that, yes, my temperature range is from here to here. But what is more essential is my temperature can physically only change at that rate. So if I measure anything which is actually jumpy, I know it must be wrong. Because there's no physical way how my system could have possibly been heating up or cooling down beyond a certain speed. Because for most of sensor modalities, you always have some idea what is physically possible. What could have changed in my environment at what speed. Cyclic redundancy check. That means it's a specific form of a Hamming code. You're adding a certain number of bits to your code word, which enables you to find 1-bit errors, 2-bit errors, 3-bit errors, depending on the size of your CSC check you're applying there. It's basically a carefully designed polynomial, which you send all of your bits through, which can easily be calculated at very high speed with possibly dedicated hardware or very simple assembly programs to do that. A simple standardized form of a Hamming code. Yep. So those are error detection means. Now assume you have found an error state in your system, something is actually wrong. The next stage is much harder. Confinement. How do you make sure that the fault affecting part can be isolated? Possibly shut down, clamped off, not used anymore. This is physically limiting the possibility of spreading your fault, or also software structure limiting the possibility of getting that further. Assessment, how bad is it? What can this cause? What has this already caused so far? And you are familiar with the next step, recovery. Backward recovery and forward recovery. We said backwards error recovery is the classical one which we have in non-real-time systems, in static environments. Database systems, always backwards error recovery. Somebody pulled the plug in the middle of it, and you have a journaling file system, you have your database which kept the trace of what's going on, and you roll back to the previous consistent state, and you start from there again. Now in real-time systems, rolling back is very unlikely, because you can only roll back things which are actually reversible. Time, to my knowledge, is not one of those. At least not yet. So everything which happens in time it's by definition not reversible, and you have to be careful to apply that one. So almost everything you have in high integrity in real-time systems is forward error recovery. You try to find a new path around this problem, rather than setting back to the beginning and trying again. It's not physically possible. Okay. That often translates into some form of mode changes, priority changes, graceful degradation, all the things which we discussed before that. Fault treatment. It's a bit of an optional step, treatment. Can you avoid this fault from happening again? And can you do this even online? Fault treatment could, for example, mean that you have hot standby systems, and this thing is faulty. Whoop, you get a new one in, fault treated by just replacing it with a fresh copy of the same thing. That only works for a certain number of times, of course, until you simply run out of hardware. Okay. So, what's a safe system? Say again? There's no such thing as a safe system.
Truly safe.
Not truly safe. Okay. What makes you say that?
Because guaranteeing safety is very impossible. You can have some level of error, something in it.
You're not planning on working in marketing, are you?
Fortunately,
Is that true? Is it impossible to build a safe system?
Well, the universe is going to end eventually.
Can you build a safe toaster?
Reasonably
Reasonably
safe.
safe.
Against everything. If you build a toaster, I'm sure I could break it if I tried. But in normal use.
setting up sledgehammers and kids with books.
Have you ever written person? I've had a few.
Okay.
Did they? They want to explore.
Were you able to
My
place
lesson. Wait, so you keep your toasters around?
There's actually a definition for it. There's a definition for safety, and that tells you safety is, as a fixed term, freedom of all those conditions that can cause death, injury, occupational illness, damage, or environmental harm. Can you build a system which lives up to those standards? Yes, of course, but this is more practically oriented, more application oriented. It doesn't say it has to live up to any kind of specification. This means that the system doesn't actually need to do anything. It only has not to kill anybody. Right? Exactly. I have a new safe toaster design. It doesn't actually toast, but it's safe.
You could lunch with someone with it. Doesn't depend on how many people use it. This plastic bag is safe if you tap it and
Exactly. Household safety is something really, really critical. And if you want to certify any piece of equipment which is allowed to be sold as a household item in most countries, it undergoes very stringent and hard testing. If you want to design and sell, for example, a ladder, you wouldn't believe what kind of testing this thing has to go through to be certified that you can sell this at Woolworth here. Devices have to be proven to be, under all foreseeable circumstances, not tripping anybody over, falling on somebody. You have to be protective against all of these kind of things. Things which can fall on you are not liked in those kind of communities. Everything which can topple over, fall over, is not good, because it can bury things, including people. So that's pretty tough.
I have one quick question about the end program.
Yeah.
If one of your programs is hit a false state, you roll back,
Yeah.
re-enter the false state. Can you just now disregard that entire end program saying something's happened, we can't identify it, don't trust it, and just trust it?
Depends on your fault treatment. Depends what kind of fault that is. It's up in your control. It's not prescribed by end modular redundancy systems that can be handled dynamically. What kind of error that is. Yeah.
If you did that, wouldn't it be bad? Because if that happened, then you can build this disregarding system. What happened if you're on your last system and you're like, oh, this one's done, so you got nothing.
Well, this is how the Ariane 5 was ultimately exploded, that you're just dismissing apparently faulty systems and just throwing them away instead of having also the backup idea that if I throw all 6 of my systems away, that's probably also not a very healthy approach, even though they may be a little bit buggy, but just killing them on the first fault is maybe problematic. Yeah. Okay. Designing a safe system which can actually be clean. What is the socially accepted level of safety? What kind of device can you sell in different contexts and environments? If you, for example, would come up with an idea today, it would be really cool to have to build a vehicle which has only 2 wheels. You're sitting on top of it somewhere in the middle, and it's really agile because it's super lightweight. It's really fast. You can bash around with that thing in traffic like mad. What do you think a safety inspector would say to this idea today?
No.
Exactly. No way in hell. Out of the question. Why do we have motorbikes on the road? No, not before, because that's it.
Because it used to be a right to not be safe.
Yes, because we are accommodated, we are used to accepting that system. It's a traditional way of transport, and we accept it as a society, the risk of doing something like that. If you come up with a new design today, it has to undergo all the safety standards which are applying to new devices, which is very different than for accepted devices. I was always
So to kind of example, the safety authorities are only allowing motorbikes because of social pressure?
Basically, yes. Basically, yes. So there is no absolute in terms of how many deaths per hour are okay. This is defined by what has already been socially accepted. But you know how many people are killed by cars on the road per year? Any idea?
In what area?
Worldwide over 1 year. Couple of million. A lot. Okay, so the real number is around 1 million people. So you're coming up with the idea is, hey, I have a brand new device. It is probably going to kill about just 200,000 people a year. They will look at you like you're suggesting a nuclear bomb as a practical household device and trying to get away with that. But the fact that we already bought into the concept that 1 million deaf people a year is okay, is acceptable.
That's not including climate change and pollution.
True. This is only people actually being smashed on the road. This is not people dying from secondary effects of the pollution which goes around that one, which is probably a lot more, as a matter of fact. Don't know. Is it orders of magnitude more? But certainly millions, yeah. Possibly an order of magnitude. Could be an order of magnitude more. Okay, so you're designing a brand new idea and device and presenting this to your local authorities, but it could possibly even kill 10 million people on the planet per year.
Yeah, that's what so actually a new device may trigger some it's made with some pulses. It will trigger some pulses.
Yeah, sorry.
It's, this comes with the counterpoint, which is the convenience and the utility of the thing that you're providing. So there's a balance between.
Okay, I want to see this. I want to see you going to the safety officer and telling him, look, it's 1 million dead people a year, but it's a very practical thing. It's really cool. It's lots of fun.
Well, you just turn around and say, we've legislated it, we've got licensing in place, we've got testing, we've given a whole bunch of we put a whole bunch of things in place to reduce the risk, then it would probably be more dangerous than if you just let it go every year. But by convincing them, I mean, like we regulate cardiacs, right? So because it makes it seem safer, but it's still ridiculously dangerous, like by the sheer numbers alone. But it seems safer because with licenses can drive with the speed limits.
But if the psychology of humans would actually go the same way of we understand how many people are dying on the roads, so we request as a society higher safety standards, which happens exactly in aviation. The social pressure for aviation is luckily very high. So these guys are playing to highest levels because they're actually mandated and legislated to do that. That these kind of failure rates are legislated on these people. They have to actually design systems to those standards.
When you say new technology, do you mean like the whole new, like a whole new car, or like, because you can have a new technology which is like part of a new car, but just like someone made an engine which is run like a car which runs water in Japan and is patented, and you can run like a car on 90 kilometers an hour for 90 minutes on like a bottle of water.
No, I was cartoonishly making up the case. If you wouldn't have any cars on the planet, and you come to a safety regulator which is used to legislating, I don't know, household ladders and push carts and God knows what, you tell them that I have this new idea about a car. That would probably not go down anywhere. If you want to put anything into a household, it's also interesting what is accepted in a household, what's not accepted in a household. Things falling over, really bad. Putting chemicals into the hands of people who have no idea what they do, okay. Because the kind of cleaning chemicals which you can buy off the shelf at Woolworths, that's actually quite potent stuff. And there's some of these chemicals which are hard to get your hands on if you work in the chemical industry, because they know how dangerous they are, and you have to get 3 copies and 3 applications and signed by your boss 5 times before you get your hands on that stuff. You can alternatively also go to Woolworths and get it off the shelf, because it's also part of this cleaning product as a subactive agent in that stuff. So the social acceptance of this is okay, this is not okay, depends very much on what we're used to and on the social environment for the whole thing. So I always found quite fascinating. You build a humanoid robot and you want to deploy this humanoid robot in a household. What do you think the chances are of this thing getting certified, getting safety clearance? So if it looks somewhat android, somewhat humanoid of some sort, it will probably be able to fall over. If it is physically able to fall over, forget it. Because the example which will be given to you, which I've seen concretely, the example which will be given to you is in households, you have little toddlers going over the ground. This little toddler is stumbling over, is just pushing against your humanoid robot. It falls over, squash. Not okay. So, really hard to get something like this into a simple household. And I think it's okay that we're quite careful introducing these environments. But on the other hand, we have to understand that the levels of safety which are applied here are socially defined, not technically defined.
I think you need to change your marketing.
Yeah.
Toddlers in the world looking at a population. Mass
How much technology do you think has been like stifled or delayed due to like the overemphasis of safety and stuff?
That's a very interesting question. So, is it hindering progress, basically? Is it hindering innovation?
People should be allowed to accept the risk, given that they're informed of this product and the other reason.
Okay. I can answer that concretely in a way that what is acceptable as a form of an airplane today? The safety standards are so high that trying to put just your control surfaces at another spot is already so adventurous that how many different shapes of airplanes have you seen over the last 10 years? They kind of all look the same. Right? Regardless from what manufacturer you're actually looking at, they all look the same. Now look at the number of airplanes, a number of different shapes which have been produced in the 60s and 70s during the Cold War phase, and how experimental they were. Yes, a few of them crashed. They didn't all work. But the innovation space, trying new things, the mindset of accepting that was completely different. So don't get me wrong, I'm not saying we have to kill more people. But there is a valid point around at what stage it is actually hindering innovation, that we cannot move anymore and change anything. Okay. Are cars becoming safer? Loaded question. Yeah? Yes?
Yes.
How? What makes you say that?
Since they brought in NAMCAP rating for Australia, for example, the testing is like 5 stars. It's like a standard technology.
Yeah. How is that tested? What is tested?
Crash survivability rate at a certain speed.
Yeah. So it's assumed that what is the relevant factor is you crash in a certain angle on a piece of metal or another reference block, and is the passenger cabin deformed from that?
Yes.
Okay. Is that everything?
You've got twice the number of crashes. Having 5% safer is not going to be.
Is it taking into account, for example, how likely is it that I crash into that thing? Just that point?
Yes.
Not at all.
Cars are getting quieter and more aerodynamic. Well, no, okay, you're driving along in a new car.
Yeah.
You feel like you're going 60 when you're going 100, mate. You're driving my car, you're going 240.
Exactly.
Terrifying.
I'm also enjoying a 1991 very low Civic, and you feel in this thing like a race car when you just go 100. Very beautiful. And you also feel the road. Do you feel the road in a current car? No, it feels more like a PS3. Right? Completely decoupled, electronic steering, and if you go through a bump, you go a little bit bob. But you don't actually feel it. You don't have contact physical to the world. So how does it relate to safety? Would it, for example, be a good idea to put windows in cars so that you can look out of them? Would you consider this a safety feature? No. No, that's outdated. You don't actually have to look outside the window anymore, right? Now, this car I drove in Europe a long time back, and a car was reversing into me, and then coming out and shouting at me how I dare to drive such a small car. And this should be forbidden. This is so unsafe. I wasn't quite sure how to take that. And I was cross-checking that. I was actually getting into this guy's car and looking through the rear window. My car was gone. He couldn't possibly have seen me. So in that sense, yeah, right. It's fine. He couldn't have seen me, and he's right to complain about this. But wouldn't you consider this car safety, that you can look outside cars? It could have been my car he crashed into. It could also have been a whole school class of kids which were not much taller than my car. And he could crash in them and say that I couldn't have seen these kids. I don't have windows in my car.
When you have self-driving cars, it tends to be safe number one.
Well, in that case, you don't really need a window, you just need an illusion of a window, right? No, if you see what's going outside, you don't really need a window. You can have cameras which just reflect, but it's like a full metal block which just gets reflected the outside world to you. So it gives you the illusion of a window, but it's not actually a window.
And cameras are not affected by sun flare, by adverse weather conditions.
Mostly it will be current conditions, but like maybe night cameras. Yeah.
Say again?
Just thermal vision night cameras out beeping in reverse.
Thermal vision night cameras. No. Because you look into the sun, you don't see little issues. Doesn't help you at all. Huh? So very simple things about cars, like for example, giving the driver a window to actually see stuff, would for me be a safety feature. For example, having mirrors which are larger than that you have a chance to see people in those mirrors. Wouldn't that be a safety feature?
Yeah.
You agree? Okay. Car manufacturers do not. Because a smaller mirror looks cooler. And it's more aerodynamic. Saves fuel. So the mirrors are pretty tiny. Now if you want to sell a truck, the safety authority tells you, bugger off with your cool little mirror. The minimal mirror size for trucks in most companies, in most countries, is well defined. You're not allowed to drive a truck on the road which has mirrors smaller than a certain size. For safety reasons. Because they know, they make it smaller, they kill more people. It's a direct relation. They make it smaller, they overlook more school children in the corner. So, okay, saving more people, making them a certain size. Passenger cars, not qualifying for that. For passenger cars, you can have tiny mirrors in there. Perfectly fine.
Does it also depend on the style of the mirror? Like most trucks have like the vertical instead of the...
And you need to have a certain style of mirrors as well. That's also prescribed in those things. But I'm not sure whether cars are getting safer in an overall picture. They're getting safer for a certain number of features which are explicitly tested, which is the crash test, survivability, so you stuff more airbags into your car, so you have tons of airbags which make your chance of surviving a little bit higher. But the chance of crashing into things also depends whether you can avoid a crash. And if I'm not seeing the road, feeling the road, getting into contact with around it, my chances of actually avoiding a crash are going down. Okay, so it's quite interesting to define what a safe system actually is. And of course, I'm completely with you about beyond a certain complexity, or I can also formulate beyond a certain amount of energy in a system, there is no such thing as a safe system. If it has a certain weight and or a certain speed, it can go boom. And this is just by the very definition of a system, beyond a certain complexity. Other more useful terms in that context, reliability, availability, safety. Confidentiality is an interesting one, which is something which we're usually not thinking about. Unauthorized disclosures is a quite interesting one. If you happen to work for intelligence agencies or for the military in one way or the other, this is actually a quite dominant thing to do. You fly your unmanned aerial vehicles someplace around, they occasionally come down, and they occasionally come down on the wrong side. If they come down on the wrong side, you don't want to surrender all the information which you have gathered with these kind of things to the wrong side. So you need to be making sure that this is somewhat safe. And also what has been discovered in war theaters in real life as well, if you have your unmanned aerial vehicles transmitting the video images in the same style as we have been transferring analog video with our FPV flying, there can be more than one receiver on the ground, which is an obvious in-your-face violation of this form of confidentiality. And so the guys which you want to observe see the same picture what you see, which is not the idea. Okay. Let me get quickly through the last section. What can you do to make it more reliable in a formal sense? Restricting your possibilities. There's the Ravenscar profile, which you're familiar with. There are also other profiles, particularly DO178B, which is a particularly high integrity profile for the aviation industry. If you program in that kind of environment, this is the language restrictions which will get prescribed. Talk about this in a moment. Or you go formal. Talk about this also in a second. You can go fully extreme, either zero footprint profile. Zero footprint means there is no runtime environment, there is no tasking, there's this super lightweight version. This is one step above assembly programming. This is really, really low level. Not very frequently used in high integrity systems. The Ada Ravenscar profile, we don't have to go into more detail here. You have seen the limitations on that one. Some of the things I'm not too unhappy about. There is, for example, no abort statement, which I'm trying to avoid under all circumstances anyway. I always have the feeling if I have to use an abort statement in my code, it's kind of surrendering that I lost control. I don't have any more decent means of designing my system. And the Ravenscar profile released me of this temptation in the first place. It doesn't allow me to do anything like that. Certification profiles. Anybody of you ever heard of these kind of standards? DO 178, common certification standards in the industry, and they are required if you want to fly anything which is mandated by the FAA or the EASA. So in other words, unless you're planning to sell your planes to some local carrier in Antarctica, you will have to go through these kind of certifications for any kind of airborne device these days. It's an interesting mixed bag of different methods. It is not strictly formal. It is not requiring you to go through formal specifications. You actually have to pay money, by the way, for these kind of standards to read them. Those are not open standards in the sense of you can just download them. But this is how it actually applies to many of these kind of standards. And ultimately it comes down to good practice, that you can convince your certification officer that he buys into that one. There's a long list of things which he will be looking into with you. But it's not a mathematical proof. There is slow migration into that direction, but it is not required for those environments. Anybody has worked? Yeah.
So why do you have to pay for those standards?
Why do you have to pay for these standards? Or because it's managed by the standard organizations, which are just charging a few bucks for that one. It's not much. But they're making a living out of that by providing this kind of service and organizing the standardization process. So they're helping also in the management of these standards, and they're charged for that. It's a bit like an editing service. If you publish in a high-level journal, then often they will charge you for the editing costs, which goes with that one.
But they're charging for actually receiving the document outlining what to do generally, and then also the actual bringing the plane and testing and having
No. They have nothing to do with that. This is just managing the standardization document. They're managing many other standardization documents in those systems as well, not only aviation safety. Who has worked with temporal logic before? What form of temporal logic? Okay, so you should all be familiar with that one. I just go directly to these temporal logics, which we have there. So that's the one you are feeling familiar with. How is temporal logic different from standard first-order predicate logic? You have these quantifiers, these classical two quantifiers here, U and S, which you can imagine as until or since, and they express temporal relations between your predicates. That's the most bare-bone version you can get. and you can reduce most other logics just on that. For comfort reasons, you usually have something a little bit more extensive, like, for example, event load temporal logic. Seen that one before? Event load temporal logic can also define intervals. So this holds true for at least this and that long, or this has been holding true since that time in the past, and continuously since then until now. So I can explicitly define intervals, which is different from linear temporal logic. Yeah?
So there's like a restriction on the L2.
Yeah, exactly. And this is what is done in the next step. You can also just, instead of explicitly having an interval and an until, you can also restrict the until, that the until and the since operation is only available to certain intervals. Okay. I trust that your predicate logic machine is still good enough that you can read something like this. Okay. This is not a logic course. This is only to show you that you can do this in the strict logic environment as well, and we are not doing linear temporal logic here or any kind of temporal logic in this course. This is only to give you the hint that this can be done. And this is actually the more pragmatic way which is being done today, that you have translation tools between your full-blown language, for example Ada, and logics which are a bit more expressive than LTR. For example, Y3 theory improver. You can directly translate between your high-level languages and the theory improver environment, verify your stuff there, and translate it back into your high-level environment, and then amend it with all the temporal stuff which you cannot express there. So otherwise you could just program it in Y3 for starters, and just compile it from Y3 into your direct machine. While you can do that, it's not going to get you the full way, because some things are just not expressible in an effective way in logic. Well, it's the complexity of the systems you have been fully formulating in LTR. What kind of systems have you been modeling? Full-scale airplanes? Yeah. If you want to verify real-time systems in, what is give me an example, what is the level of a practical real-time system which you can do in LTR in full today? Say again? An elevator. And you go, wow. Yeah. It's about on the level of, say, a medium complexity pedestrian traffic light crossing. That's about the level which you can fully model and verify in those environments. Simple state machine systems, and we rip out in our flight controllers these modules, which can then be verified, but they're expressing a subsection of the whole thing, and you don't get a lot further than that. For example, the whole translation of your GPS signal, your GPS coordinates into a navigation system, I don't think you would dare to go with LTR on something like that. You stick with actually the state machine modeling on that one. Okay. So, and that's concluding reliability. Should we do the course in 10 seconds? Course in 10 seconds. That was good, right? What have we been doing? We have been discussing real-time programming languages. What do you need to do to operate, to design things in a real-time environment? We have been talking about physical coupling. How do you connect, take measurements, sense your environment? You remember these considerations which we had there? How do you select your sensor? How do you understand your sensor? What is the physical modality? How do you translate it to something? Then we have been converting to that. What are your AD converters? What is a converting device, interface device to your physical modalities? How do you handle the electrical aspects of that? How much do you need to understand of the electrical signal characteristics of the whole thing? How much do you need to understand of the translation abilities? You have seen all AD converters known to man, and you can choose now, educate and freely, what you want in those conversion environments. I think I posted also on the forums at some point that there is the boundary has been pushed to a few more bits on video cameras now. So the next blockbuster movie you can expect to have half a bit more color depth resolution, which you will undoubtedly immediately recognize. But we are pushing this by quarter bits per decade in terms of precision. This doesn't jump very, very quickly. But you have some idea what that means. You know what effective number of bits are, how this relates to your practical systems, how far you can push these things. Right? So, time and space. We understood a little bit what it means to handle time, how to interface with it. And in broad strokes, how to satisfy timing requirements. Asynchronism, quite important chapter to understand that not all of your systems are synchronous processors, but you need to handle things which are happening asynchronously in your environment. Coming from a concurrent programming environment, that should come fairly natural, but you have had a lot more details about how to handle this in practice, and you have been handling this in your assignment as well. You were forced to. There's no way how you could avoid this in your assignment. Right? We quick forwarded through the whole synchronization chapter. Don't have to lose any more comments on that. Scheduling is quite important, that you understand how different real-time scheduling is to desktop operating scheduling, and what possibilities you have, what guarantees can you give there. You saw examples of scheduling environments which are completely deadlock-free. Gives you possibilities which are quite different from desktop scheduler environments. You understand what different priority ordering schemes imply, which priority ordering schemes are optimal, and what that means. You know the difference between scheduling environments which can, load your CPU in full and can guaranteed handle your requests, and scheduling environments which are having more slack and more feedback, more fallback possibilities for your practical system. Resource control. Resource control implied reclaiming algorithms of all sorts and a number of different categories for synchronization primitives. And finally, reliability. To look at the whole system, what can you do from an engineering and computer science perspective to make your system more dependent? And here we opened up again to the whole world of physical possibilities, including social possibilities, what you can model to make your systems more safe. Right? That's it.